Hello friends, welcome to Tips and Tricks in Mathematics. This is for class 12 students and the topic of discussion is application of derivatives. This is an introductory video on this topic. What is the physical meaning of derivative? We have done derivative, first derivative, second derivative. What it does and why it is required. What are the basic applications of derivative we will be discussing here. Now consider a function like this. Let us draw a graph. X y, y is f of x, and let us draw some function like that. Now the question is, what is derivative of this function? Let us consider a point here, a. Then we draw the slope of this curve at this point. The slope of the curve is the derivative of this function. So how does it matter? For example, if you consider another point b here, the slope will be like this, or the tangent to this curve. So the slope is changing at different points on the curve. So derivative is also changing along the function. So at different points, derivative will be different. Now the question comes, what shall we do with this derivative? Where does we use? Now consider, instead of xy graph, x is distance or x is time, x-axis is time and y-axis is distance. Then what is the derivative? Dyy by dx, or d distance we generally call with symbol s and this with time, ds by dt. How distance is changing with time? So this is nothing but the velocity. So the derivative of distance time curve at each point will give the velocity. So velocity at a, velocity at b point is given by this derivative. Now you may be wondering, instead of s and t, if we have x-axis t and y-axis say velocity, then what happens? Then we'll get dy by dx as dv by dt. That is how fast the velocity is changing with time. This is nothing but acceleration. So if you are given a velocity function, say velocity x equal to something you are given, then the derivative of this function dv by dt, or this is a function of t, say 5 t plus 7, then dv by dt is given by 5. This is nothing but the acceleration of the body. So we see that the derivative is important. It has physical meaning. Now question of what is increasing and decreasing functions. Let us draw two functions. X is an increasing function. As x is increasing, y is also increasing. It makes sense, but question comes, how do we mathematically say that this is an increasing function? We cannot plot a function like this always. We may not be knowing. For example, if a function is given as y equal to x power 4 plus 3x cube plus 2x square plus 3x, some function is there, you cannot plot this, but you want to know whether this function is increasing or decreasing. Is there any condition? Yes, there is a condition. Condition is dy by dx is greater than 0. This is, or we can also write f dash x is greater than 0. It makes sense. For example, this is an increasing function, so the slope is, this is positive slope. This slope is positive. If you take this point, this slope is positive. If you take this point, this slope is positive. All are positive. This is the condition for increasing function. So whenever the first derivative is greater than 0, the function is increasing. You don't have to plot always. Now consider what is the condition for decreasing function. X y equal to f of x. So this is a decreasing function. Okay, from the plot we can understand it is a decreasing function. But what is the criteria for to show it in mathematically? So that is given by f dash x or dy by dx less than 0. Physically, what does it mean? Suppose you want to find derivative here. You see that the slope is downwards, it is negative. Similarly, at this point, At this point, slope is again downwards negative. So this is the condition for decreasing function. So if derivative is positive, the function is increasing type. If the derivative is negative, the function is decreasing type. Now let us take one example. Let us find this function is given. We want to find whether it is increasing or decreasing, what it does. Let us do f dash x, 3x square minus 6x plus 4. We can write this x square minus 2x plus 1 plus 1. 4 we have written 3 plus 1. So 3 is taken as common here. What is this? Equal to 3. What is this? X minus 1 the whole square plus 1. So for all real x, this f of f dash x is always greater than 0. Yes, even if x is negative, this term will be positive. X is 0, we will get at least 1. So f dash x is always greater than 0. Hence, f of x is an increasing function for all r. Let us take another example. Here f dash x will be 2x minus 4. Let us equate it to 0. So we get x equal to 2. What happens when x is equal to 2? This term is 0. But what happens when x is greater than 2? What happens to f dash x? When x is greater than 2, f dash x is greater than 0. You put 2.1 or 2.2. This term will always be greater than 0. What happens when x less than 2? F dash x will be always less than 0. So x greater than 2, function is increasing. Function is decreasing. Actually, this function is like that. This is a quadratic function. We will get like this. Here x equal to 2 is the point beyond which function is increasing, and below this function is decreasing. Now we'll come to another important point called as maxima and minima. Let us plot a graph. Function. We are plotting a function. This is some complicated function x y equal to f of x. This is that function. Now we see that it has got so many maxima. These are called the local maxima. Local. So many peaks. Similarly, it has got some minima also. This is called local minima. The maxima means where the function maximum occurs. Local minimum means where the function minimum occurs. What do you observe at the all maxima and minima points? What is the specialty you are seeing? We see that the slope or these curves, these dotted curves which we are plotting, their slope is 0. So dy by dx equal to, or say f dash x is 0. So whenever we get a condition where slope is 0, we get either a maxima or minima. This is very important. So whenever a function is given to you, you want to know whether it has a maximum or a minimum, and you want to find that point. We just find the derivative of that function, equate it to 0. You will get some x equal to some values you will get. So those are the points. Those will be the points like this: x1, x2, x3, at which the function maxima or minima occurs. This is called as the first derivative condition. But a question comes, I want to find maxima, but you are telling me maxima or minima. How do I get it? How to distinguish between maxima or minima? Or suppose I want to just find minima, but this condition is for maxima also. So how do we do? How do we proceed? Then we come to the second derivative test. This is very important. In the second derivative, we have the function f of x. We find first f dash x equal to 0 to get maxima or minima. But if it is maxima, then f double dash x should be less than or equal to 0. So this is condition for maxima. So from the second derivative test, if we find the second derivative less than 0, then that point x is maxima. Similarly, if f double dash x is greater than 0, that x point is minima. So the first derivative gives a condition of local maxima or minima, and the second derivative test gives whether that is a maxima or a minima. Let us take one example. We can take x square minus 4x plus 6. We have seen f of x. Let us find f dash x. 2x minus 4, let us equate to 0. So implies x will be equal to 2. But 2 is a point at which maxima or minima occurs. But which one? Whether it is maxima or minima, we will do with the second derivative test. So this will be 2. 2 is positive. 2 is greater than 0. So x equal to 2 is a point of local minima. We have seen it earlier. We have seen this plot. This x square minus 4x plus 6 is plot is like this, where at x equal to 2 minima occurs. So we have found the condition also using second derivative test. Friends, with this we conclude this video. Please like and subscribe my channel so that in future more videos can be released to you instantaneously. Thank you very much, friends.